It's 2 a.m. at a nuclear construction site in eastern China. Engineers face a nightmare lifting a 2,000-ton reactor vessel in one unbroken piece, where a slip of just 5 centimeters could mean a $100 million disaster. But what seems impossible is now routine. Thanks to 3 Chinese crawler cranes so powerful, their combined market is worth over $15 billion, and their reach has upended the global order of heavy lifting. In just 15 years, China flipped the world's crane industry from Western control to its own dominance. How did a nation once dependent on German and American rentals come to build the largest, most advanced lifting machines on Earth? The answer begins with 3 titans of steel and a race to conquer the laws of physics themselves. The Sany SCC36000TM stands at the edge of the nuclear exclusion zone, its twin lattice booms rising above the containment dome. This is the machine that made China's modular reactor dream possible. Rated for 3,600 metric tons, with an 88,000 ton-meter load moment, the SCC36000TM was built for one job: lifting the heaviest nuclear modules on Earth with surgical precision. 8 crawler tracks spread its weight across the ground, each segment engineered to handle forces that would buckle most steel. The boom reaches out nearly 80 meters, supported by a herringbone base, an unusual design chosen for one reason: stability. Nuclear construction in China shifted almost overnight from slow, piece-by-piece assembly to a new method: giant modules, weighing nearly 2,000 tons, prefabricated at ground level, then lifted whole. Western cranes could not guarantee the 5-centimeter accuracy needed to thread a reactor vessel through a containment ring. The SCC36000TM's laser guidance system does. Operators, trained for 500 hours, sit 85 meters above the ground, eyes fixed on a digital display as the load swings into position. Every movement is tracked by gyros and strain gauges, each reading feeding into an adaptive control system that can halt the lift if sway exceeds safe limits. In 2015, at a coastal site near Haiyang, the SCC36000TM placed a 1,850-ton reactor vessel into its cradle, with a margin of error smaller than a child's shoe. The job took under 4 hours. Where Western cranes needed weeks of incremental lifts and endless checks, Sany's machine finished in a single shift. The design is not just about brute force, it is about precision. Each module, each weld, each sensor tuned for the nuclear sector's unforgiving standards. The SCC36000TM did not just meet the challenge, it redefined what was possible in nuclear construction. Now every new plant in China's fleet begins with the arrival of this machine. XCMG's XGC88000 arrived on the scene in 2013, not as a nuclear specialist, but as the world's new petrochemical workhorse. This machine is built for raw throughput: 4,000 metric tons of lifting capacity, 88,000 ton-meters of load moment, and a main winch with the muscle to pull 160 tons in a single line. Where others rely on fleets of support cranes for assembly, the XGC88000 uses its own triple-engine system to erect itself, cutting setup time by nearly a fifth. Each Cummins diesel powers a separate hydraulic circuit, one for the boom, one for the winch, one for the crawlers, so the crane can move, lift, and adjust all at once. The 2013 propylene tower lift in Shandong put this crane on the map. A single vertical column, 2,155 tons, hoisted to over 110 meters in one continuous motion. No mid-air handoffs, no piecemeal welding at height. The job, which would have taken weeks with conventional cranes, finished in hours. Operators credit the XGC88000's self-assembly for the pace. Boom sections slot together without auxiliary lifts, guided by sensors and remote cameras, while the crane's own weight anchors each segment in place. On site, The main hook block alone weighs 45 tons, heavier than most city cranes can even lift. The XGC88000's design allows it to work in extreme conditions, from -40 degrees in Siberia to the scorching heat of the Middle East. Heated hydraulic reservoirs keep the systems responsive even when temperatures drop, and the modular crawler pads spread its weight so it won't sink into soft ground. Between 2018 and 2021, this model logged more than 200,000 tons, lifted across 26 major projects. No Western crane matches that tempo. Every hour on the job feeds operator feedback straight to engineers, who push firmware updates and tweak assembly protocols in real time. For China's petrochemical boom, speed and self-sufficiency aren't luxuries. They're the new standard. The XGC8000 didn't just raise the bar, it built a new one. Sany's SCC45000A stands alone at the summit of heavy lifting. This machine is not just the largest crawler crane ever built, it is the world record holder, rated for a staggering 4,500 metric tons. Its reach climbs to 690 feet, higher than a 60-story tower. To move it, a convoy of 247 trucks hauls the parts across provinces. 68 loads just for the counterweights, each slab weighing 65 tons, stacked and aligned by laser to within half a millimeter. The total counterweight tips the scale at 2,200 tons. Assembly is an operation unto itself. 30 days of non-stop work, 45 specialists on site, every stage tracked and double-checked. The boom alone takes 2 weeks to piece together, each section stress-tested before the next goes up. Once built, the SCC45000A can walk under its own power, shifting its 8-crawler base across a site while carrying a 1,000-ton load. The hydraulic system runs 12 separate circuits, each with its own sensors and emergency shutoffs. During a major lift, the crane burns through nearly 2,400 liters of diesel in a single shift. But the true breakthrough is flexibility. Engineers can reconfigure the crane mid-project, switching from maximum capacity to lighter, faster setups without tearing the whole machine down. On a Yangtze River site in 2021, this modular approach let the same crane handle both the heaviest initial lifts and a rapid-fire sequence of smaller ones, cutting project time by weeks. The cost of deploying the SCC45000A is immense, nearly $3 million just to assemble and prepare the site. But for megaprojects where a single failed lift could mean disaster, there is no substitute. Each deployment is a spectacle of logistics and precision, a demonstration of what is now possible. With this crane, Sany has set a new global benchmark, not just for brute force, but for the orchestration required to control it. The question now is not just how big a crane can be built, but what kind of nation can build it. On a construction site outside Yantai, a project manager stares at a schedule that's already slipping. The problem isn't labor, or even weather, it's the crane. The new modular reactor vessel, weighing nearly 2,000 tons, sits finished and waiting, but the only machine capable of lifting it is still somewhere in Europe. The rental contract for a Western crawler crane stretches on, draining $40,000 a day from the project's budget. Every week lost means another $1 million gone, and the plant's opening pushed further into the future. This wasn't a one-off crisis. By 2010, China's nuclear and petrochemical ambitions had outgrown the world's supply of super-heavy cranes. Modular construction demanded single-piece lifts, reactor domes, coal chemical towers, entire process modules, each weighing as much as a destroyer. Traditional cranes, built for smaller segmented lifts, couldn't handle the load. Even the largest Western models topped out at 3,000 tons, and there were only a handful available worldwide. With China's construction pace, projects lined up behind each other, all waiting for the same machines to arrive by ship, be rebuilt from scratch, and certified again by foreign engineers. Delays of 3 to 6 months became routine, and costs soared. One missed lift could mean a domino effect. Labor idled, permits expired, contracts renegotiated under pressure. The stakes climbed with every new plant. Nuclear sites demanded flawless precision. A 2,000-ton module, swinging even a few centimeters off target, could damage containment structures and force months of rework. Petrochemical megasites faced similar risks. A distillation column, lifted in one piece, had to be set exactly into a web of pipe racks and supports, with no room for error. Project managers described the feeling as playing chess with a single queen. Every move depended on equipment they did not control. Foreign dependency was more than an economic problem. State planners saw the risk. When a country's energy security, industrial output, and even national prestige hinge on a handful of foreign-owned machines, the vulnerability is obvious. Western suppliers, facing their own backlogs, gave priority to European and American projects. Chinese sites, even with cash in hand, waited and waited. The frustration ran from site foremen up through ministry offices. In internal memos, delays were labeled strategic bottlenecks. The urgency was impossible to ignore. Without a domestic solution, China's entire modular construction revolution threatened to grind to a halt. The pressure that built up in these years would soon force a new approach, one that would change the global crane industry forever. The bottleneck was clear. China needed not just bigger cranes, but a way to build them on its own terms. The answer came from the State Council in Beijing. In 2006, super heavy crawler cranes were quietly added to the national priority list, classified as key enabling technology. This single designation set the policy engine in motion. The Ministry of Industry and Information Technology drafted technical roadmaps, spelling out milestones for lifting capacity, safety, and modularity. The National Development and Reform Commission unlocked the capital. State banks received orders to offer loans at rates as low as 0.5%, sometimes stretching repayment over 15 years. For Western firms, every new model meant a battle for boardroom approval and a business case that paid off in 5 years. For Sany and XCMG, the mandate was different. Build the cranes, whatever it takes, and the state would carry the risk. Between 2015 and 2025, direct research and development funding for super heavy cranes reached $2.1 billion. This money didn't just cover blueprints and prototypes. It paid for entire test yards, 50 hectares of concrete pads, climate chambers, and stacks of steel weights. Engineers ran cranes through overload cycles, freezing rain, and simulated typhoons. When a prototype failed, the response was not to shelve the project, but to rebuild and try again. Early boom designs that cracked under stress were torn down, redesigned, and back in testing within weeks. Western competitors, bound by quarterly earnings and investor patience, could not afford this pace. Local governments joined the race, each vying to host the next flagship factory. Suzhou, and Changsha offered free industrial land, 10-year tax holidays, and subsidized power lines. Provincial officials promised streamlined permits and fast-tracked environmental reviews. In return, manufacturers pledged jobs, exports, and technical leadership. The result was an industrial cluster: steel mills, electronics plants, hydraulic specialists, all within a day's drive of the main assembly halls. Component lead times shrank from months to weeks. When a new alloy or sensor was needed, suppliers delivered overnight. Preferential procurement rules completed the loop. State-owned energy giants were told to buy domestic whenever possible. This gave Sany and XCMG a guaranteed market to scale up, refine designs, and build a track record before facing foreign competition. For every crane exported, dozens more worked the home front. logging hours and feeding data back to engineers. In this environment, failures were tolerated, even expected. What mattered was the learning curve. The state's patient capital absorbed the early losses, betting on global dominance in the long run. This was not the invisible hand of the market, but a deliberate push, turning national need into industrial muscle. A shipment of high-tensile Q690E steel leaves Baosteel's rolling mill at dawn, bound for a fabrication yard less than 200 kilometers away. In Changsha, Sany's engineers are already waiting, blueprint revisions in hand. Here, nearly 9 out of 10 crane components are sourced within a day's drive. The proximity is not just convenience, it's a feedback loop. When a prototype boom section cracks under test loads, replacement steel arrives in 3 weeks, not 3 months. In Europe, a similar fix could stall a project for an entire quarter. On the assembly floor, robotic welders run X-ray checks on every joint, aiming for reliability rates above 99%. Operators from recent job sites drop in, carrying notes from last week's lift, hydraulic lag on a 2,000-ton module, a sensor glitch that flagged a false overload. These details feed straight to the research and development team. In the past year, Sany's super heavy cranes have averaged more than 50 major lifts each, an operational tempo that would take Western machines 5 years to match. Each job is a live test, every close call a lesson. One veteran operator remembers a near miss, a counterweight shifting half a centimeter during a night lift. Within days, engineers installed new auto-leveling sensors capable of detecting ground settlement down to 2 millimeters. Lead times shrink, design cycles tighten, and the cranes themselves evolve, shaped by the relentless pace of real-world demand. July 1999. In Milwaukee, 3 ironworkers die when the big blue crawler crane collapses under wind and shifting ground. The disaster leaves twisted steel draped across a half-built stadium, and every crane engineer in the world takes note. In China, these lessons become blueprints. Modern super-heavy crawlers are built around triple redundant load indicators, each sensor cross-checking the others. If a reading disagrees, the lift stops. 5 wind sensors scan the boom at different heights, ready to halt operations if gusts rise. Ground settlement is tracked by lasers that detect a 2-millimeter dip, enough to trigger a controlled pause. Crews in Jiangsu run through these protocols before the 2021 Shenghong hydrogenator lift. The XGC88000, hauling 2,600 tons, rotates the vessel from horizontal to vertical, then threads it through a steel maze. Real-time feedback keeps the vessel steady. The lift finishes 10 days early. No incidents, no delays. In Pakistan, the SCC36000TM faces crosswinds at Chashma nuclear site. Adaptive controls adjust winch speeds on the fly, holding a 1,850-ton dome steady as wind gusts hit the site. The dome lands exactly on target. Offshore, in the East China Sea, a marine-adapted crawler places 1,800-ton wind foundations, using wave-dampening legs and corrosion-proof hydraulics. Each project is proof. Safety is not just a checklist, but a system, hardened by tragedy and tested in the field. By 2025, the numbers tell a new story. 2 decades ago, Western firms controlled nearly 4 out of 5 super-heavy crane contracts worldwide. Now, Sany and XCMG alone account for more than 60% of the market. Industry analysts project that by 2030, 3 out of every 4 cranes in this class will be Chinese-built. On construction sites from the Persian Gulf to the Andes, Chinese crawler cranes are now the default, often arriving as part of the financing package for ports, refineries, or nuclear plants. Industry estimates suggest over 800 Chinese crawler cranes operate abroad, supporting more than $100 billion in Belt and Road infrastructure. Operator training has scaled to match. Since 2020, more than 12,000 international operators have completed certification in Chinese facilities, learning on the same equipment that now sets the global benchmark. Every new project, every successful lift, deepens the network. Spare parts, maintenance contracts, and technical standards all tie back to Chinese manufacturers. The next horizon is already taking shape. Rumors circulate in trade journals about a 5,000-ton hydrogen-powered crawler crane under development at XCMG, targeting offshore wind and zero-emission megaprojects, possibly launching as soon as 2027. If true, it would not just extend China's lead in heavy lifting, it would redefine what's possible in global construction. The monopoly is no longer just about who builds the biggest machine. It's about who controls the future of megaprojects, one lift at a time. In 2005, Western companies controlled 78% of the global super heavy crane market. By 2025, Chinese manufacturers will hold 61%, with over 847 Chinese crawler cranes now operating in 67 countries. This shift was driven by state-backed investment, a surge in domestic demand, and the ability to integrate steel production and rapid field testing, compressing decades of engineering progress into just 15 years. Archival records confirm $2.1 billion in research and development funding and documented safety innovations adopted after studying past disasters, like the 1999 Big Blue collapse. Yet some policy details and internal test results remain classified. Today, China's cranes are not just machines, they are tools of global influence, deployed wherever Chinese-backed infrastructure rises. As plans for a 5,000-ton prototype advance and thousands of operators train in Chinese facilities, the world's heaviest lifts increasingly depend on a single nation's industrial engine. The story of these cranes is a blueprint for how strategic necessity, state policy, and relentless engineering can reshape a global industry.